So this is lecture 24. Let me say it's part 1. And so what I'm going to do in this lecture is simply do a couple of problems which will help us understand the material that we've been studying so far about forced RL circuits. So here's the first example. Let's do this example. Here's a 50-volt source. Here's another source. Which is 50 U of t volts. There's a 2 ohm resistor, a 6 ohm resistor, and an inductor, 3 henries, and the question is that I want to determine determine I of t through the inductor for all time. And then plot the response. And then plot this response. Okay. So, in order to solve these kinds of problems, as I mentioned to you in my previous lecture, it's always best to look at the problem from minus infinity to 0 minus first. All right? So that is, you look at the circuit at t equals 0 minus. All right. So let me just say the following. Suppose we are looking for the time period for t. Suppose we are looking for the time period for t less than 0. Okay? Suppose we are looking for this time period. Well, if you look at this circuit, the circuit then reduces to the following. It's this 50-volt source on the left. The second voltage source is a short because for t less than 0, u of t is 0. So the second source is a short, and then I have the 2 ohm resistor, and I have the 6 ohm resistor. And of course the circuit has been sitting here from minus infinity to 0 minus, okay? And it's a DC circuit, and therefore the inductor is a short, Okay, so the point I'm making is that I only need to look at the response of the circuit um, at t equals 0 minus, because from minus infinity to 0 minus, it's a DC circuit problem. So let me draw the circuit first. If I draw the circuit, it's simply the following. It's the 50-volt source. It's this 50-volt source. There's this 2 ohm resistor, and then of course there's this 6 ohm resistor, but the inductor is a short. All right, so that inductor is a short, and this current here is then I at 0 minus. So if I wanted to determine what I of 0 minus is, well, that's very simple. Then I at 0 minus is simply equal to 50 over 2, which is equal to 25 amps. Okay? All right. Now let's look at the circuit for t greater than 0. Okay, so let me use all this space over here on this page to kind of discuss this next component of the problem, and that is I want to now look at the time period for t greater than or equal to 0. Okay? For t greater than or equal to 0, the circuit is the one that we have on the left. Basically, well, let me redraw it so that you see it. It's this 50-volt source, and this 50-volt source is now in the circuit. Okay, this is 50 volts because U of t for t greater than 0 is 1. And then of course I have the 2 ohm resistor. I have the 6 ohm resistor, and I have the 3 Henry inductor. Okay? And so I know this is a circuit which has an inductor, it has resistances, and it has forcing functions. Okay? So immediately, without any thought, I know the following. I know that the solution I of t, this is all for t greater than or equal to 0, must equal some I natural of t plus some I forced of t. Okay? And I also know that I natural of t, I natural of t is of the form a e to the power of minus t over tau, right? Here are my two unknowns, A and tau, and in the above expression, so is IF of t at this point unknown, all right? And so the next step in the game is to determine tau, all right? There's only one inductor, so I know L. What I need to do is reduce the rest of the, I need to determine the R equivalent, all right? I need to determine the R equivalent. So what I do next is I kill the circuit, all right? Kill the circuit. Kill the circuit. By which I mean short circuit all independent sources. So if I short circuit the 50 volt source and the other 50 volt source, then what I'm left with is the following. I'm left with this 2 ohm resistor in parallel with the 6 ohm resistor, okay, and this is in parallel with the 3 Henry inductor, and of course these two resistances are in parallel, and so this is nothing but the equivalent resistance R equivalent, if you like, which is equal to 6 2s are 12, 6 plus 2 is 8, so it's 12 over 8, it's equal to 3 over 2 ohms, and there is my L, which is 3 Henries, and I know that tau is equal to L over R equivalent, and so this is equal to 3 over 3 over 2, and so tau equals 2 seconds, and tau inverse equals 0.5 second inverse. All right, so I now know that my natural solution, therefore my natural solution In of t is equal to AE to the power of minus 0.5 t. Okay? Now there are two other quantities which are required at this stage of the game. I need to determine the constant A, and I need to determine the forced solution I sub f of t. Okay, so I need to determine this quantity, and I need to determine this quantity. All right, and so let's go on to the next page. But before I go on, let me just say the following. To determine the forced solution, remember what the natural solution is doing. The natural solution is the transient solution between where it was, or the circuit was at 25 amps, right, that we did at t equals 0 minus. Then there's this transient to where it is finally going to go, where the 50 volts plus the 50 volt sources are pushing this circuit. So I now want to look at the circuit. Let me look at this circuit. This is again for t greater than or equal to 0, but I want to look at this circuit for t tending towards infinity, for large t. And let me draw the circuit for large t. For large t, the circuit is the following. I have this 50-volt source, and I have another 50-volt source. I have a 2-ohm resistor. I have this 6-ohm resistor, and then I have the inductor. But for large T, this is a DC circuit, and therefore, once again, the inductor is a short, and so this current, which is what I want this current at infinity. But that's very trivial. The current I sub f at infinity is simply 100. 50 plus 50 is 100 divided by 2. The 6-ohm resistor is short, and so this gives me 50 amps. All right. Notice that this is a constant and that the forced solution is exactly known. All right. So what is left? Now we know that our solution I of t is now equal to the natural solution, which is a e to the power of minus 0.5 t plus the forced solution, which is 50. All right, in of t plus if of t, that's that solution. The only thing remaining now is the determination of the constant a. And now I know the following. I know that I have determined the current I at 0 minus to be equal to 25 amps on the previous page. But this is a current through the inductor. So the current at 0 minus must equal the current at 0 plus. So therefore, I now substitute this fact that I at 0 plus, or I at 0, it doesn't matter, I at 0, which is 25, is equal to a, because the exponential is 1, plus 50. Therefore, a equals minus 25. And therefore, for t greater than 0, my solution for t greater than 0 is I of t is equal to 50 minus 25 e to the power of minus 0.5 t. Okay? So let me draw this picture for you now as to what is happening. Maybe I should write it down here first. Let me rewrite the total solution here. The total solution is the solution is I of t equals 25 amps for t less than or equal to 0, and is equal to 50 minus 25 e to the minus 0.5 t for t greater than or equal to 0. All right. Let's plot it. Let's plot it. So here's my nice plot. Here's I of t. Remember, I want the current for all time, and so here's t. Where's the circuit sitting from minus infinity to 0 minus? Well, it's sitting at 25 amps. Where is the circuit going? Well, it's going to 50 because this forced solution is 50. So it's going to 50 amps. How is it going to 50 amps? Well, it's going this way. All right. So that's the solution to the problem. Now, one can, to conclude this problem, one can write the expression for the current in a much more sophisticated way by using the unit step function. And so let me write the function for you over here. It's I of t. Let's put that there. I of t equals 25 plus 25 times 1 minus e to the 0.5 t times u of t amps. And this is a much more sophisticated way of writing this, because you can see for t less than 0, u of t is 0, so the result is 25, which is what we had above. And for t greater than 0, u of t is 1, and so it becomes 25 plus 25 is 50, and the minus is there, so it minus 25 e to the minus 0.5 t. Okay? All right. Let's now do another problem. Okay? Here's another example. And this is a slightly more, this is a slightly more, or at least it seems a slightly more difficult problem. And the problem is the following, that I'm going to let me draw it here. I'm going to apply a pulse function, and I'm going to define all these quantities in a minute. I have a simple RL circuit. All right, this is a simple RL circuit. This is R, this is L. And I'm now going to apply a pulse function to this RL circuit. That is, I'm going to apply this function. This is V of t. This is t. I'm going to say, let's apply 0 t naught v. Let's apply this function to the RL circuit. All right, and we can and I want the response of the circuit. That is, I want the current I of t for all time. Okay, all right. So that's the question. I apply a pulse to this RL circuit, and I want the response of the circuit to this pulse. So first, let's write down the expression for v of t, as we did in the previous lecture. V of t is simply v times, because I can represent this pulse function as a sum of unit step functions. So this is u of t minus u of t minus t naught, close parens. Okay. So how am I going to solve this problem? Well, let's draw the circuit. Let's draw the circuit a little bit more fully first. Okay. And the way to do it is the following. Using this expression out there, the circuit becomes the following. It's this is v u of t. Oh, this is becoming too big. Oops. And I can say this is plus minus, and then I can say this is minus v u of t minus t naught. Okay, and then I have my r, and then there's the L. Okay, this is L. And so that's the circuit I have to solve. But this circuit, in order to solve this circuit, I see there are two voltage sources. So why don't I use superposition? I'll use superposition. So I'll calculate the response of one source, and then I'll calculate the response of the second source, and I'll add them up. All right? So, to be pedantic, let me do the following. This is v u of t. This is R, this is L, and I will call this the response of the circuit due to Vu of t as I1 of t, and then I'm going to add to it the response of the circuit to minus Vu of t minus t naught. This is R. This is L. And this current, this response, I will call I2 of t. And therefore, I of t is going to be, by superposition, I1 of t plus I2 of t. All right? Okay. Now, we know the solutions. We know the solution for I1 of t. And we know the solutions for I2 of t because I worked them out for you in the previous lecture. So let's just use this information that we have. So let me go on to the next page. And it doesn't hurt. Plus minus v u of t. This is R. This is L. And this is I1 of t. And I can immediately write down the following statement. I can say I1 of t is equal to V over R times 1 minus e to the power of minus R over L t for t greater than 0. I can say greater than or equal to 0. All right. What's the solution for this is I1 of t. What about this case? What about the solution to this case? This is plus minus. This is V u of t minus t naught. This is R. This is L. And this current here is I2 of t. And what is I2 of t? Well, I2 of t, this is a minus sign here. This is a minus sign here. Let's not forget that. Did I forget that on the previous transparency? Let's go back. No, I didn't. That's good. That's good. Okay, so let's go back here. So it's minus Vu of t minus t naught. Okay, so the only difference is, number one, the sign is negative. So there's your negative sign, V over R times 1 minus e to the power of minus R over L. And let's be a little careful. When does this source come on? When does this source come on? This source comes on at t naught. Okay? So the argument here is t minus t naught, close parens, and this is the case for t greater than or equal to t naught, because this source comes on at t naught. U of t minus t naught is 0 for t less than t naught. Okay? All right. So now I have the solution. I have the total solution. Let's write it down. I have the solution. So here's the solution. Yeah, let me do it here. Solution. The solution is that I of t equals V over R 1 minus e to the power of minus R over L t for t lying between 0 and t naught, right? because that's the only source. V of u of t is the only, this response I1 of t, maybe I should write it down here. I of t equals I1 of t plus I2 of t. That's my superposition. And so I of t, that's the solution, that's the response of the circuit, is that it's I1 of t between t lying between 0 and t naught. Okay? But then, for t greater than t naught, there's also I2 of t floating around. Okay? For t greater than t naught, both I1 of t and I2 of t exist. So let me write that down. Let me write down I of t equals I1 of t, which is V over R, times 1 minus e to the power of minus R over LT, plus I2 of t, because now we're talking about t greater than 2 naught, okay? So which is minus V over R times 1 minus e to the power of minus R over L t minus t naught, close parens. This is for t greater than t naught, because for t greater than t naught, both responses are there. Okay, so let's simplify this last expression. And so again, to be a little pedantic, let's do it. What the hell? It's V over R minus V over R e to the power of minus R over L t. That's the first term. And then we have a minus V over R, right? And then the minus and the minus is a plus, so then it becomes a plus V over R e to the power of minus R over L t minus t naught. So you see that this V of R and this V of R cancel out. And I then have, let me write it down here. I have this minus V over R e to the power of minus R over LT, and then I have a plus V over R. Now let's break up that exponential function. It's e to the power of minus R over LT times e to the minus times minus is a plus, so that becomes a plus e to the R over L R T naught. Okay, and I should have done this more to the left, but let me see if I can squeeze it in here. So let me combine these two terms, and this simply becomes V over R e to the plus R over L T naught minus 1 times e to the power of minus R over L t. And this is really evident. I mean, from the left-hand side, you can see all I've done is e to the power of minus r over lt is common to both, and v of r is common, so I've pulled all that stuff out. Okay, so this is the result. This is for, let me squeeze it in here, for t greater than t naught. Okay, now let's just for a second look at this last expression, and what you see is that this term over here, this term is simply a constant. This is a constant. V is a constant, R is a constant, L is a constant, T naught is a constant, 1 is a constant. So this quantity here in curly parens is a constant. So it's a constant times a decaying exponential. Are you with me? Okay, so for t greater than 0, the response is an exponentially decaying function. For t lying between 0 and t naught, it's an exponentially increasing function. Not exponentially increasing, it's 1 minus an exponential function, increasing. All right, so let's do the following. Let's plot this. Let's plot this. Okay, I'm going to make 2 plots for you out here. All right, and just to make the point, I'm wondering if I should. No, it doesn't matter. I won't rewrite the equations. But let me draw 2 graphs for you. Here's one graph, and let me plot the total response. By the way, this is the response of the RL circuit to the pulse function. Well, I tell you what, it doesn't matter. Let me rewrite. What the hell? Let me rewrite the solution. Okay. So I'll say I of t. Let me rewrite it. I think it'll be clearer. Is simply v over r times 1 minus e to the minus r over L t for t lying between 0 and t naught, n is equal to a constant which happens to be v over r, and let me put it in a parens just to, and this is e to the power of plus r over L t naught minus 1. This is in, excuse me, minus 1 close round parens close square parens e to the power of minus r over Lt for t greater than t naught, and of course is equal to 0. Let me improve that. Is 0 for t less than 0. So this is my solution, and now I want to plot this function. Okay, I want to plot this function. And I want to plot the function for 2 cases. For the first case, I want to plot the function for which tau of course is L over R, right? L over R. In this case, I want to plot tau to be half t naught. Okay, So I'm going to plot that. All right. So this is 0. Let's make this T naught. This will be 2 T naught. Okay. And all right. So here goes, and let me also make this point over here, which is 1/2 T naught, which is equal to tau. All right. So the solution says the response is 0 for t less than 0. I don't have to explain that point. I mean, that you all understand. There's no voltage source, so there can be no current from minus infinity to 0 minus. Okay. Now let's look at the expression for the time t between 0 and t naught. Well, if you look at that expression, that's exactly the expression we had for a simple RL circuit with a voltage source. And so what is that function? What is that function trying to do? Well, it's trying to go towards its asymptotic limit. That is for large t. So if you look at the first expression for large t, that exponential dies down. So it wants to go, I have to be careful, I'll draw it carefully. It wants to go to V over R. All right. And how does it want to go? Well, it goes as 1 minus an exponential function. And we also know the following, that at t equals tau, at t equals tau, it's gotten to 63.2% of its final value, which is 0.632. So I know this point, right? So it's trying to go to V over R. And how is it trying to do that? It's trying to do that this way. It goes up like this, and it gets to this point, right? It gets to this point at t naught. But let's assume that the other response wasn't there, then this would simply continue on its merry way to V over R. But at t naught, the second, that exponential function, that constant times an exponential function, comes into play. And so the function decays exponentially. You see that? All right. Let's do the same thing. For the case let's do the same thing for the case, this is I of t, for the case when tau is 2 t naught. Okay? And so let me draw this. This is t naught. Oh no, I drew it much bigger. Let me try to make the two parallel, similar. Let me use the same types of scale. No, maybe I can't do that. let's see, this is T naught. This is 2T naught. And unfortunately, I can't get to 3T naught. But let's assume, hold on. Let's assume this is 3T naught. And this is my T. Okay. And what is my circuit doing? Well, as before, the current up to 0 is 0. So this is 0. This is V over R, right? So let's draw this as V over R. This is V over R. Now tau is 2T naught, so 2T naught is tau, right? And so at 2T naught, let me see, is this is, yeah, I used 2 boxes, okay. So this is tau. This is 0.632 V over R, 63.2% of its final value. And so what the response function, the response is doing is the following. It starts out at 0, from minus infinity to 0, and then it starts to take off towards V over R. It starts to take off towards V over R, right? And if the second response wasn't there, this would go on its merry way towards V over R. Okay? And at this point here, it would have its value of 63.2% of V over R. But at T naught, the other exponential jumps in. Okay? Because this thing comes on at T equals T naught, the solution is an exponential function. And so that's what the response looks like for tau equals 2T naught. And you can see that the smaller the time constant, the more quickly the circuit responds, more steeply responds to trying to get to V over R. Okay? The larger the time constant, well, you see what figure B looks like. This second figure on the right looks like. Okay. One final important point which you need to tuck away for the near future. Okay? And that's the following. What have we seen so far? What have we learned so far? Okay. We've learned that if we have a DC source in the circuit, we introduce a DC source in the circuit, bingo, the response, any voltage, any current, is also a constant. All right? That was the first third of the course. Then in the last few lectures, we've introduced exponential sources. And what did we see? We saw that if you have an exponential forcing function, you also have the responses, any voltage, any current, which are also exponential. But now you're seeing the following. Your forcing function in this last problem was a pulse, was a pulse. Okay? And what's the response? The response is not a pulse. You see what I'm saying? So later on, we are going to learn how to deal with situations in which the response is different from the forcing function. All right? So let me, I thought I would do this too today, and that is, let me summarize. I think, oops, one of you said the summaries. Summary. One of you said summaries were helpful, so I decided I would summarize. So here goes. So step one, I'm just going to give you these steps for solving the circuit problem. So the step one is draw circuit at t equals 0 minus. Okay? This is a DC circuit with all inductors shorted. Okay? And let me talk about the, oops, this is not working. Determine inductor current. Let me call it IL at 0 minus. All right. Step 2, consider the circuit for t greater than or equal to 0. The solution is of the form IL of t equals IN of t plus IF of t, the natural and forced solutions. And this is of the form A e to the power of minus t over tau plus IF. Well, let's leave it as IF of t for the time being. Okay. Step 3, kill circuit. Kill circuit. What do you mean by killing circuits? Short circuit all independent voltage sources. And later on, when we talk about forced RC circuits, You know that killing a circuit might mean also open circuit or currents, independent current sources. But for the time being, determine L equivalent and R equivalent. Obtain tau as equal to L equivalent over R equivalent. That is, when you kill the circuit, you want to reduce it to an RL circuit, some R equivalent, some L equivalent. Okay. Step 4. Consider the circuit for t tending towards infinity. Once again, this is a DC circuit with all inductors shorted. Okay. Solve for IL of infinity. This is a constant. Okay. Step 5. Since IL at 0 minus is equal to IL at 0 plus, the current through an inductor cannot change instantaneously. Determine the constant A, determine A using this initial condition. Okay, so you have then IL at 0 equals A plus IL at infinity, and this immediately leads to A equals IL at 0 minus IL at infinity. Okay. 6. The solution is then IL of t equals A, which is IL at 0 minus IL at infinity e to the power of minus t over tau plus IL at infinity. Okay. This is kind of writing it out a little formally, but you understand that these are the steps that we are going to follow in solving any particular circuit. So let me stop here as 24 part 1, and then in part 2 I'm going to do another problem, but with regard to a capacitor. So we'll be talking about RC circuits then. All right, that's it for today. Take care.